Okay. So yeah, good evening. This is our 7th tutorial session on NPTEL course on computational quantum mechanics. So in today's session, we'll be reviewing objectivity, virtual work principle, work conjugates, Piola-Kirchhoff tensors, decomposition of stresses, and some things about objective rates. Okay. So before that, what we do is let's review what was discussed in our previous session. Just in the previous session, we had not actually completed it. So let's just go through some of the ideas that were remaining. Okay. So we'll start with. So let me start with what do we mean by objectivity?
So are we discussing that the last week's?
Yeah. Yes.
So objectivity and virtual work, is it?
Yeah. So objectivity, just a brief review as to what we were doing. So in objectivity, what we're looking at is some of the ideas. So first of all, objectivity. Objectivity. Yeah. So essentially, one of the things, the way we build objectivity is we first start with a undeformed configuration, or what we call as the reference configuration. Apply some forces and tractions and moments and look at the deformed shape for the deformed configuration. So if this is omega, or we have been using B, so script B naught, and this is script B. And this is we just set up the canonical basis E1, E2, E3. And let's have a particle here whose material, what you call Poisson vector, is denoted by capital X. And then the corresponding material point after it's subjected to the what you call to the external, to this applied forces and moments, then it occupies a material point, a space in the deformed configuration, which is parameterized as small x vector. Yeah, these are just points. So we had material point. After deformation, it became spatial point. Just terminology. And the mapping function, what we call as deformation mapping, is given by psi. Okay. So psi takes an argument capital X vector, which is the material point, and it's parameterized with respect to time, because it's time which decides, or time or some time like quantity. Sometimes what happens is, okay, we are doing something known as a very quasi-steady analysis, right? In quasi-steady analysis, what we do is we apply forces, but in small increments. There, the increment acts like time. So like whenever we subject a structure to large loads, we cannot do it directly because then this numerical system will just crash. So we have to use techniques known as under relaxation and apply load incrementally, like delta F till we reach the final load. So that analysis we call as something like quasi-static analysis. Okay. Just because of numerical sensitivity. Like I had faced this problem during my project work that I did. So you have to do it incrementally. And then eventually, so in that context, time actually is this increment acts somewhat like time. So that is what it is. Yeah. So now we have this Poisson vector x naught, and now what we do is let us rotate. You see, right? There is a relative motion. Say if you have a frame and an object, either you can rotate the object, keep the frame intact. Otherwise, rotate the frame, keep the object as it is. They are equivalent, right? From a relative, from principle of relative motion, they're just equivalent. Yeah. So here what we do is, just to reduce our burden, we will keep our coordinate system as it is, rotate and translate. So this is what we call as superimposed. And this is, remember, this is all in virtual. We are doing this virtually. We are just doing this virtually. It's just building ideas. So we are just this we call as superimposed rigid body motion. And if you look at the literature, right, in quantum mechanics, you'll find this term a lot. This complete phrase itself, we call it SRBM, superimposed rigid body motion. And usually all the stalwarts of quantum mechanics, they always use this word. So this phrase. So if a book doesn't use, then I think it becomes doubtful that why didn't they use this particular phrase? Because it conveys everything that we are superimposing something on already deformed. So this is deformed configuration, actual deformed. Then we apply some sort of a rigid body rotation and translation, which is given by x tilde. So the material point becomes, it's just the same this one, but it just rotates and translates. So this we call as x tilde is equal to qx. Q is a proper orthogonal tensor. Isn't it all that q transpose q is equal to I, and the determinant of q happens to be 1. And then this plus some constant c. So c here denotes the rigid body translation, isn't it? So rigid body translation, and this is known as this q is rigid body rotation. So rigid body motion actually consists of two components, rotation and translation. And usually this translation will be homogeneous translation in the sense that it will apply equally at all the material points. So which means that we are applying throughout, we are translating the entire body. All the points have the equal displacement, and then we can rotate. Yeah.
Krishna, just I mean, I think I
Sure,
understood.
sure,
Just want to clarify for myself. I
sure,
think the
sure.
B and the next superimposed thing, they should look same, no? As in
Yeah, let
you
me
redo it, but
just.
you can actually
Yeah,
copy it and paste. That's
yeah,
what you
exactly.
just should rotate
Yeah,
it, right? Yeah.
right,
Okay.
right. I'll
Okay.
just do that. Yeah, I think that's it. It's a very important thing here. Copy and then paste it. Paste. Okay. So okay, I'll just pick this. Done. Okay, I'll just. Yeah, usually this, right? Microsoft PowerPoint has all
Paste.
these.
Yeah. Good. No worries. Yeah. Oh, we can't
Okay.
move it now, like anymore.
Yeah, it looks like, yeah, let me just try to select it. Yeah, let me show up. Damn it.
No worries. It's okay. It's okay. Just asking. Yeah.
Okay, yeah. So okay, let me just call it. So this happens to be B, and this let's call it B tilde. Say after rotation, it's just B tilde. So what I'll do is right now I'll just try to draw this somehow.
Yeah.
Just yeah. So this we call it B tilde, script B tilde. So and the material point which was x vector here now becomes x tilde vector, isn't it? So
Yeah.
from now we begin our study. So what we do is from going from the initial configuration to the deformed configuration, our deformation mapping f double f tensor was parameterized by del psi by, I mean, was defined as del psi by del x vector for any x vector. And so after deformation, what I mean after imposing SR after SRBM, what we have is we have f tilde is equal to psi, and I'll just call it as a partial x vector tilde by capital X, and then we'll use the chain rule. So it becomes by x vector dot x vector by x vector, isn't it? So like this is for a particular x vector, this for particular capital X vector. Now what we see is partial q tilde by partial q, since we knew that c vector does not depend on position, isn't it? This c here, this one doesn't depend on position. So it means that if you take partial differentiation with respect to x vector, it will result in null tensor, isn't it? Because there is no is independent of x. So all we will be left with is just q, and partial x by partial x is nothing but f, because it's we already defined here. So which means that after imposing after imposing this S, what we call SRBM, our deformation gradient becomes QF tilde. So this is the rule, isn't it? This is the rule here. isn't it? So what we do is that is I'll rewrite this because that's the most fundamental idea. So we have this. Now what we do is let's start.
Actually,
Yeah,
I mean, I don't know how much relevant it is, but if you go back to the previous slide,
sure.
so it is not just qx. I think it should be like q times q minus q center of mass of the deformed body, and it's like is you understand what I'm trying to say?
Okay,
So the
okay.
x
The thing is,
tilde
okay.
is equal to, which is I remember this equation. I asked the same question in my quantum mechanics class as well.
Yeah.
And so you understand what I'm trying to say? If you just put
Right.
qx,
Yeah.
you won't get back q tilde. So actually should be center of mass minus x, like rotation about that
Exactly. Yeah.
local body vector and
Mhm.
plus c. See, you
Mhm.
understand what I'm trying to say?
That's what you will see, right? That is actually just a way of making us very confused. That's what I learned from a biomechanics class. I think that doesn't give us
Yeah,
anything.
but still it will
So,
be zero because it is q times q center of mass. Center of mass is constant, so it will be zero,
yeah.
right? When you take
Yeah. So
derivative with respect to x, and which is true. I
right.
mean, yeah.
Right.
Yeah,
Yeah.
yeah,
So essentially, what we are trying to do is we are doing rotation with respect to the basis itself, to the original basis with respect to this.
okay.
So it's because that this rotation is any tensor is invariant with respect to coordinate system, right? Isn't it? So no matter where you apply, so if q doesn't happen to be a function of x, then it can be applied anywhere. And
Okay.
anyway, the thing is, we can say either you can take q with respect to center of mass, then it will be slightly different q.
Okay.
But that will all that q will also happen to have all those orthogonality properties like q transpose q is equal to identity. You see,
Okay.
right?
So
The
yeah,
properties
yeah,
will
yeah.
always remain. Yeah. So
Okay. Yeah.
that's why yeah. So because I am aware, I think I have understood what you were saying. But
Yeah.
the thing is, yeah, it's most of these things are equivalent in that perspective. Yes.
Yeah.
But this relation right here, this is the most important relation we'll find in
Okay. Okay.
SRB, and we'll always. But the thing is, it's ultimately F which gives us the something some information about deformation.
Okay.
And ultimately, the entire quantum mechanics is based on deformation, isn't it? There is no deformation, no stress, nothing. We are discounting residual stress and all, or some other stresses due to constraints. But apart from that, elasticity is based on having some deformation measure. Okay.
Yeah.
Yeah. So now what we do is let's just look at some of the other quantities, what we call as like what are the uh, conditions, right? So we know that any segment, dx vector in the deformed configuration, say this is the segment we are looking at, dx vector, and this one was before deformation. It was something here, so it was d capital X vector before deformation. So then we know that any fiber element, right, dx vector is equal to f into dx
D
transpose
capital
dx,
X. Yeah.
isn't it?
Yeah.
Now what we do is let's use this idea. So what we do is say we have dx transpose dx. So this gives us f dx transpose f dx, and this comes out to be dx transpose f into dx vector, isn't it? So this is the roughly the some of the
Yeah.
measure that. Now what we do is let's repeat the same thing with dx tilde transpose dx tilde, and we know that dx tilde is given by f into f tilde into dx vector, d capital X vector transpose, or even what we'll do is let's have something like okay, let's just use the f transpose itself here, and dx and f, this one f tilde again, isn't it? So it's like f, both are f tildes. So now what we get is dx tilde and then f tilde transpose f tilde and dx. And then what we do is we substitute qf transpose. So then f tilde transpose becomes f tilde q transpose, sorry, f transpose q into f, and then dx vector. Now we see something interesting coming up here, isn't it? That we have something called as q transpose q.
As I know.
Yeah, that's I, isn't it? So that's I.
Yeah.
So all we are left with is dx transpose f dx. Now you see some commonality between the two, right?
Yeah. So even in the rotated superimposed rigid body motion, is that right?
Yeah,
Superimposed rigid body motion configuration, the
exactly.
deformed fiber length is same,
Is
because
remains
as
constant.
as as it should be, because we are only rotating the body, right? Okay, the straight has
Right,
to be
right.
same. The
Yeah,
deformed end has to be
yeah,
same. Awesome.
yes, yes. So that is what we are saying, that okay, it's all about that the magnitude or the norm, to be more precise, norm of the vector doesn't change. Norm of a fiber element length doesn't change, is invariant with respect to SRBM. So this is the idea here essentially. So that is what we are doing our SRBM for, isn't it?
Yeah.
So what now next step we do is duplicate here. Now let's try to determine something like here that, okay, and let me again slightly modify this equation here, this one here. Not modify, just put things into perspective. Let me take it q into psi plus c. Just because ultimately x vector is nothing but psi, right? Psi vector. And I'll just call it x tilde as q, call as this psi tilde. So
Okay.
just small, just change. This is just because psi determines the deformation mapping, so it holds. So it's like we are dealing with functions or mappings rather than a particular point, isn't it? So now what we do is, let us have that one. Uh, let's have our deformation mapping in the in the SRBM. After SRBM is psi tilde is equal to q psi plus c vector. Okay. Now we have something known as a velocity in deformed configuration. So velocity is given by del psi by del t, partial psi by partial t, isn't it?
Yeah.
And now what we can do is, uh, we can have this one. We'll just substitute the value here. In the lectures, they have not done this general, but we are just, let's make it more general.
Sure.
So what we are doing, trying to do is, now we can apply the chain rule, isn't it, for every term? I mean, in the first term. So
Yeah.
here it becomes q dot psi plus q partial psi by partial t plus partial c by partial t, isn't it?
Okay.
So yeah, what we see is this term, I think we are familiar. Partial psi by partial t is,
QU.
yeah, this is
QV.
v. No, yeah, exactly. This is q, exactly qv. So what we saw is v tilde is q dot psi plus c dot.
Hmm.
However, when we take a look at our deformation gradient, it looks like after SRBM, this is what the relation should be. Because, or maybe even let's consider some vector. So since we had considered this d vector, right, dx vector, let's come back here.
Hmm.
So dx tilde is was given by f f tilde f tilde.
QFD capital X. You can write that way, right?
Exactly. Yeah. So it's like q into d tilde. मतलब dx x vector, isn't it? So this
Yeah.
is the relation. So it means that every vector deforms in this manner. It's just the rotation. However, this is not equal to qv.
Wait. Can you go back once?
Sure. Yeah, here.
Uh, so you missed F here, right? No, you didn't. Okay.
Yeah, no,
Yeah. Okay.
yes,
Cool. Okay.
exactly.
Yeah.
Yeah.
Q small x. Yeah.
Right. So what we saw, right, that the vector deforms by just q. It's just multiplying it by q That gives us the
I mean, does that mean it deforms? It just rotates, right? I mean, Q
exactly.
is,
Yeah,
because it depends on the Q properties. I think Q is something like, I think it has some properties. If you apply, it doesn't
right.
actually change the magnitude of D capital X, but it just
Exactly.
makes
Yeah.
the
Rotation
orientation, right? That's
doesn't change
what
the
we have to.
magnitude. Yeah.
Yeah, so I think the
Yes.
magnitude of Q times dx, if you take the magnitude of this thing, then,
Right.
right? Yeah. Okay. Okay. Let's continue. Okay.
So what you see, right? That this statement you take a look, right? So
Okay.
v dot v tilde dot. I'll just write it. V tilde dot.
Okay.
It's not v tilde. Sorry, it's just v tilde. Sorry, just v tilde.
Yeah.
So v tilde is q dot psi plus qv plus c dot. However, we learned that the vector should transform after SRBM as just q multiplied by the original vector.
Uh,
Like that is the rule for a vector, and that should be possible for any vector
that's correct. That's right.
to
That's
be
right. But
to be
that's
considered
correct.
objective. To be considered. So like this does not satisfy.
But no, oh my God, this is. I mean, I don't have
Yeah.
that much basic to say any comment here. Like,
No, no. The thing is, these are just rules. Just rules. Just rules.
that's true, but
Like
it depends on. So what you're saying is the velocity vector is staying in this frame, like in the
yeah.
in the modified frame, and you're saying
Right.
that whatever the vector which when it goes to the new frame, which is q, let us say that it is called x tilde, it should
Yes.
just translate as xv or x small p or
Yes.
x
Should just
like it
rotate
should be
means
q times. It
magnitude.
should just be q, right? Okay, q
Ex-
times
Yeah.
multiplied by
Exactly.
that.
Which means that is the principle. That's our assumption that after objectivity implies the what you call the conservation of certain quantities.
So yeah, I have a comment. I don't know. You might say
Sure.
how this is right or
Sure.
wrong.
Sure.
Now you
Sure.
explain
Sure.
it. I understand, but I want to give a comment here. So
Sure.
if you have a body rotating, like if the rotational motion, if there is a
Hmm.
rotational motion of the body, of
Hmm.
course the point with which we are dealing with will have this additional rotational velocity when you look at when you see from a frame, right?
Yes.
So
Yes.
so
Yes.
say that you have a dog which is
Yeah.
going like there's just like you have a vector which is a dog.
Okay.
Say that it is moving, okay,
Right.
the body is not rotating, it's
Yes.
just there,
Yeah.
then the velocity will be simply dx by dt. But
Right.
once you have the rotation as well,
Yes. Hmm.
then you should also consider the rotational motion of
Yeah.
this whole frame as
Yeah.
well, right?
The only
So
thing
the
is,
equation which is written here actually I think
yeah.
comprises of all this stuff. No, I want you to, yeah, I want
Yeah.
to
The
hear.
thing is, we are doing this virtually. We are talking, right? Things are virtually. The thing is, SRBM is done on a deformed body. We are not applying any force. So the thing is, no force means no change in momentum, isn't it? We are just slightly rotating it. Okay, for simplicity, and that's what you'll find in books. They take to be C to be constant. Okay, so that we this term also gets removed.
Mm-hmm.
Just for simplicity, we just remove this term to be 0.
Okay.
Now also the thing is, yeah, we should after because this is a virtual operation, right? This is just doing some SRBM on a deformed state. So we are not applying any force. We are just rotating it. So everything, the norm, the fundamental assumption is that the norm of the vector should not change. However, what we see is the norm of the vector is changing after SRBM in a virtual setup. In a virtual setup, where do we get extra force, right? Like I mean acceleration. Where do we get it? That's that. Why does the magnitude of the vector change? I mean the velocity change because there should not be any such change, isn't it? Because we are doing just in a virtual environment. There should not be just. It should just rotate because remember it. We are not doing this for a large distance. It's just a small rotation, small translation motion, just like what we do in linearization, right? We just make some small perturbation. So here it's just like rigid body motion perturbation, small perturbation. So the velocity should not change, the magnitude should not change to be called something as objective. So that is the goal here. So say what if we had we were just rotating the frame and having the body it is. So the thing is velocity vector should have just rotated. It should not have changed its magnitude.
Yeah, the solution term should not be there. That's what you're saying. Okay.
Actually, that is assumption. Remember that it's an assumption. Like many a time it will feel okay, it's not physical, but that is as an that is an assumption of objectivity. So it's like the fundamental assumption of objectivity. Without this assumption, then we don't have the concept of objectivity. Objectivity assumption in objectivity is
Like any vector should only like
exactly
QV. That's it. You should not have
right.
if you have additional
Vectors.
terms, then it's not objective.
Yes, yes. So this is
Okay.
the assumption in objective that vectors should deform by any vector. Say I'll take v only here. Should just deform. Should just rotate. Magnitude should be preserved. Must be preserved. Sorry, must be preserved. Then it's not. If it's not, then it's not objective.
Okay. But here it is fading now.
Yes, that's why it's that the velocity is not an objective tensor.
Okay.
So it's like v velocity is not an objective tensor. Velocity is not an objective tensor. Is not
So
an object.
F is an objective tensor. That's what I see. Right?
Exactly.
F is
Yeah.
objective.
F is tensor. Yes. Objective
Okay.
vector. So the
So
idea
like,
is
see,
yes, yes. Please.
so
Yeah.
in our, I mean, I'm going a bit future lectures. I remember that
Right.
like
It's all right. Yeah.
you have strain rate.
Yes.
Okay. In strain rate, you have velocities.
Yes. But you have
In rate
gradients.
rating, yeah, exactly. That's what I mean. You have
Yeah.
gradient of, I think is defined by L dot, if I remember right.
Yeah. And
Equal
yeah,
to
we'll
some,
come it to later. We'll just come
I
there
don't know
also.
if you can discuss objectivity of such. We haven't discussed
Yeah, of
anything
course.
regarding to. So, but
Of course.
anyways, I just want
That
to,
is in the
giving an idea.
right.
Okay,
Sure.
awesome. I understood this. Yeah.
Okay. So this is like the fundamental assumption, like it's all the theory is based on this assumption. So like if you don't assume this, then the entire objectivity part is like, then it's just there is no foundation to begin with. Yes. So this is the fundamental assumption that we make in for objectivity, study of objectivity. So which means that if velocity vector is not an objective, which means that we cannot cast any such relation between stress and strain using velocity.
Okay.
That's the idea, isn't it? Because objectivity now, if we just so now if we
exactly
just
right.
yeah, exactly. So if we now just extrapolate our ideas, it means that even after doing rigid body rotation, it should not affect the relation between stress and strain. That's the idea. So it means that in our relationship between stress and strain, we can never use velocity in its current form. Because it's not objective. The thing is, it will say after rotation, you will say that, okay, where is this extra stress coming from? This should not come.
Yeah, exactly. Yeah. Awesome. Okay.
So now we built, let's move forward from here. And from here, all these ideas start falling in place, right? So now we see that, okay, what about Green-Lagrange tensor? Or Cauchy-Green tensor for the material. Cauchy's tensor was given by Cauchy-Green tensor was C
F transpose F
is equal to exactly F transpose F.
Yeah.
Fine.
I think Cauchy-Green is left or
yeah,
right?
this is the right Cauchy-Green. This is the right Cauchy-Green.
Right Cauchy, because F is right side. Okay.
No, because when you decompose it, we use RU and U is on the right. So that's how we remember it.
Yes, I remember that. Yeah.
Yeah. And in left Cauchy-Green tensor, we decompose F as VAR. Yes. So this is the basis of left and right.
So I forgot. So I just want to repeat that. So this
Sure.
F equal to RU.
Yes.
So that is, do you call that? So in that U is called right.
It is known as right stretch tensor.
Stretch tensor. And did we discuss C equal to F transpose F in the previous?
Yeah, we have discussed here. We have discussed because it comes in handy to give us something known as a deformation measure. Like the thing is, we use this. We just use this relation. This is just a defined quantity. Just defined. We are just defining it. So this is known as right Cauchy-Green tensor. And what we do is, why not find the value in its after SRBM? So it becomes C tilde, and then we have F tilde transpose F, and then we substitute all that QF transpose QF.
Okay.
Isn't it? Now what we see is we have F transpose Q transpose Q and F.
Same.
So So this is identity. This is the same. This is the same. And so which means that C is an objective tensor. Now you'll ask, okay, why this discrepancy? The thing is, it also depends. Now, when you look at C, C always stays in material configuration, because how did we arrive at C in the first place? We arrived by taking dx vector dot dx vector is equal to f d capital X. This is just transpose. Let me use a transpose into f dx transpose, and this one was given as and f transpose f and into dx vector. Is it not? Now what we see is this we defined as Cauchy green tensor. Now what you see, the property of Cauchy green tensor is if there is just pure rotation, in that case f will be equal to just r from this decomposition, because u will be identity, just pure rotation. Then in that case c will be equal to identity. So now there is a hidden idea here, that which means that the norm of any vector dx or capital X dx vector will not change if there is just pure rotation, isn't it? So that's the idea here. So which means that, and ultimately what we see is dx vector. Let's go further to understand this in more detail. Let's do something like minus dx transpose dx here. This gives us dx transpose, and here, right here, we can fit capital I, because it's just identity when we can fit anywhere, right? Wherever it's valid operation. So like if we put I here in between dx transpose dx, then it won't change the relation, is it? Because I into dx is dx only. Okay, let me just expand it. Yeah, I think then things will become more clear. So let's have this one as so it was. I'll just call it as it is. Okay, let me just have
So
dx.
like
Yeah.
I actually I forgot the last tutorial, which is a big problem. But anyways, I'm trying to ask, why are you doing dx transpose dx in the first place? Is that a
Okay.
magnitude? Is a magnitude actually? I see
Yeah.
that.
Now we'll see the why we are doing this, right? Why we're
So
doing is.
you're checking if this thing, this tilde will make any
No, I'm just
difference.
trying to, yeah, just trying to make you understand, right? The meaning of C. Why do we need C? Or what does C do?
Okay.
Okay, just what does C do, isn't it? So what I have done is I have just put an identity here, here.
Okay.
It doesn't change the relation. So all that we have is dx transpose f transpose f minus I into dx.
Correct. And there's a C,
Isn't
right?
it?
Is a C? F transpose is a C?
Yeah, yeah. Now what we'll do is let's also do one thing. Why don't we divide both sides by d capital X divided by d capital X d
The
capital X.
initial length. You mean initial length?
Yes.
Okay. Hmm?
Now you see, right? It gives us some idea about the change in length,
Yeah. Yeah.
isn't
The
it?
strain. The
And
strain, right?
yeah, it gives us something about strain. And what we do is just for the sake of why we add half always comes in handy later. Like why do we
Okay.
add half,
Cool. Okay.
isn't it? So then what we do is we take it inside and call it dx transpose by dx transpose dx half f transpose f minus I into dx. And this quantity we call as Cauchy green tensor. Sorry, or green Lagrange tensor, because this gives us an idea of the change or the rate of, the change. So like this is a tensor itself. So it gives us rate change in with respect to every axis, change of an element oriented along some axis in with respect to other axis. This gives us the full 3x3 picture.
Okay.
And and then what we see is now we can clearly see that.
Oh, okay. So it's like if you take an element in x direction, say that you take
Right.
something like if you take like 100,
Yes,
multiply
yes,
with
yes.
it. I think he
Yeah,
will tell you how that one like element in one direction will change.
yeah,
And when
one
you
direction will change.
010, E will give you how in that direction the element will change.
Exactly. Yes.
Okay.
So
Okay.
say right, even if the deformation, right, the deformation taking place in more than that one particular unit direction that we're considering. Say if dx is aligned along x e1 axis, however, after deformation, it will be aligned in some other way. Need not always be
Yes,
along e. So
that's
which means that
correct.
we are getting component of this strain vector in every directions. And that's how you define shear strain and all that strain. You know that not everything can be normal strain, right?
Yeah.
So E gives us a complete
Can we
picture.
see some examples regarding this, if
Yeah,
possible?
yeah, of
I think
course,
I'm
of course,
really
of course.
interested. Not now, not now. When you complete
Sure,
the
sure,
this.
sure. Yeah, yeah,
So you mean E equal to half C minus I is like,
yeah.
this
Right.
is the best thing actually. It's actually, is that Lagrangian or is I
Yeah, this is
couldn't
known
follow
as
it? Is it
green Lagrange.
Lagrangian?
Green
Okay,
Lagrange
because
tensor.
we're dealing with D capital X, not D small x. That's why it is
Yeah.
Lagrangian, right?
Yes, yes, yes.
And maybe Green might have invented this. That's why we call it Green
Yeah, green
Lagrange.
Lagrange. Yes. Now you see something clearly, right? You see something here going on. What is the
So
base? What is the reference with which we are computing the change in length?
okay, the first length, no, first dx,
Yeah,
yeah, D
exactly. You
capital
see,
X.
right?
Yeah.
So which means that E is the rate of is the change or the changing length with respect to the original configuration. So
Correct.
which means that E exists in material configuration. E exists in the in the reference configuration.
Yes, I mean, I think just want to interfere. I don't want to
Sure,
say it
sure.
is wrong, but I think it is differential, not because I think it is maybe due to we are taking the initial length.
Yes,
Also, if you look at the equation E, D capital X transport times E times dx, E
right,
is dealing with the referential frame vector D capital
right,
X.
exactly.
I
Yes.
think don't you think because of that we should say it, E is more. Uh, I think I agree with because of the initial length.
Uh-huh.
Maybe it
This
should be
was
that
just
as well. Oh,
yeah. This was from a what do you call just philosophical perspective. Now
maybe
we can
yes,
even
yes.
show that
You're
mathematically.
right.
We can
You're
show that
right. Yeah.
mathematically also. How did we define deformation gradient?
FD capital X
Parse,
by D small x by capital X.
isn't it? Isn't it?
Yes.
And we had talked that any reference, any vector in the spatial configuration is defined. I mean, using indices, we use lowercase indices. So it's just like parcel xi.
Yes. By
So
capital
like
XJ.
x,
Mm-hmm.
small I, and then
By capital XJ.
small e. And for any vector in the material configuration or the reference configuration, we denote with respect to capital J or capital indices.
Mm.
And we had talked about how we define gradient, right? So the gradient of any vector, because ultimately this is gradient operation.
Yeah.
So gradient of any vector v is defined as parcel vi by parcel capital X. Because gradient, I mean, again, the thing is how we define gradient. Gradient should always use something called subscript because we always want to know with respect to what gradient.
Yeah. Yeah.
So the thing is the what you call the more mathematically better way of representing a gradient operation should always be with respect to what. So that we put in subscript. So here with respect to capital X, which means with respect to the material frame or the material coordinate. So this means that E1 EJ, and here you say that J is capital. This just mind you that this is just mathematical representation. It has no logic. I mean, like if we find logic, obviously it has the way the more we get used to it. But the thing is, it doesn't have any physical meaning. This is how we do. Like this is how we represent because F maps something in the reference to something in deformed, isn't it? So like mapping deformation gradient has to exist in both the configurations because it maps. Right? I mean, I must insist that please understand this. This is the most fundamental thing that why F should live in both because it maps something to something in material to something in reference. Sorry, something in spatial. Why? We have this reference B naught. This is B. This is D small x vector. this is t capital X vector. So after we apply f on this to get this.
Yeah.
So the operation is f. Okay. So that is the thing. So which means that it should just like when I mean just talk about linear algebra, right? So when you map, say they have a function f from Rm element of Rm to something in X is y is an element of Rn. Now when you write, when the thing is then y is the output. Okay, y is output, X is input. Fine. What is mapping it? Because I must tell you that this is linear transformation. So this is linear transformation. So what we do is this is n, this is m, this is n, and this is n. So there must be some linear transformation operation which takes a vector existing in Rm space to something in Rn space. So the transformation, say if you represent it by capital A, the dimensions will be n cross n. See, right? N cross n should be the dimension of the operator. And likewise, just extrapolate here, but in a more abstract sense, like we are mapping something from a dimension dx, so to speak, or material dimension to something in spatial dimension. Something initial to something. So there is what we have is then this one will also be. Some books prefer to call any coordinate system in a deformed, I mean, in the reference configuration to be capital E. The thing is both are equivalent. I am not using this because it conflicts with the small a, I mean with the green Lagrange tensor. So I'm just using E and everything denoted by the indices. So what I want to say is EI is equal to E capital I, EJ small is equal to E capital J, EK is equal to, or yeah, is okay. I think I'm just using dummy
What do you mean
indices.
by equal
So
to?
E1 is equal to E spatial is equal to E1, sorry, E1 reference is equal to E1 spatial. That's what I meant to say. So which means that, okay, let me make it things more clearly. Which means that,
But they're not equal, no?
yeah, which means that now the thing is we are considering the same coordinate system, right? Isn't it? What we see even after deformation, we are using same coordinate system. We are not changing the coordinate system.
Yes, yes, we are. Yeah.
And
That's
we are
right.
using canonical basis. Canonical basis won't change, like
That's
no
correct.
matter,
Okay.
isn't
Okay.
it? So now what we do is now let's take F transpose F. Okay, now let's use some tensor algebra here. Now the transformation, I'll just call it, I'll denote it using two different. So in this case, let me use xi capital J ei cross E capital J transpose. And here let me use LM. Okay, so like parcel x L by capital X M and then EL E capital M. Now after transformation, what happens is either we change the order of here, this what you call it, me using different color. Either we choose, either we interchange I and J. That's one way of taking transpose and keeping this intact. The other way is we just change the order here and we'll keep this one intact. So it's like one way is, so we'll use the easy way because both way will give us the same results, but let's just use the conventional way. EI. So this is the transpose of F. Okay, and then here this side will remain as it is.
If you take transpose, I'm just wondering, you shouldn't
Yeah.
you?
What is transfer? This one, right? Transpose. Transpose is the row becomes columns and columns becomes rows, right?
Yeah, yeah. Okay, cool, cool. Yeah.
Isn't it? So what
I
was
have to
supposed to be
practice my
rows?
tensors, man. Yeah. Anyways,
No, no,
yeah.
it's
That's
all
right.
right.
That's
It's all
right.
right.
That's right.
It's all
That's
right. So,
correct. Yeah.
so what was rows before became columns? What was columns before became rows? And the thing is, this will automatically become matrix because this is just the representation. If this changes, the order changes here, you will see that after we actually write in matrix form, it will be transpose.
Yeah, yeah. That's right. Yeah.
Isn't it? Now what we do is let's use some properties of linear algebra. I mean, oh, sorry, this tensor analysis, right? So this is xij dot. Dot is yeah, let me not use confuse you. Just x capital M, and then we call it ej bun ei el bun e capital M. Now there is a property here. If you have things arranged in such manner, then this is equal to ej bun em. Just look at the last into ei dot el. This is just
Yes,
the
because
property of tensors,
conical delta. Okay.
tensor analysis, isn't it? Now what we say is, you know very well, this both exist in the same frame, right? Both are small indices. So this one from the property of Kronecker delta, like if you take say e1 dot e2, it gives you delta e1, right? It becomes delta I. If I happens to be equal to L, then it becomes 1, isn't it? Like e1 is
Yeah, yeah.
e1 dot e,
Then
isn't it?
then yeah, you can change xl to xi, dou xi, dou xl to xi.
Exactly. Yeah, that's what we are doing to do, right? So it's delta I. Wherever L is there, we will replace it with I. And you see something is going on here. Xj partial xi by partial xm into it's just take a look at all the indices. I gets compact. I mean, this is what you call all. It gets added out, isn't it? There's a repetition, like it
Yeah.
gets summed out. And when you take a
Yes.
look at the representation, take a look at the representation. This is also in reference. This is also in reference.
Yeah.
So which means that C exists in material configuration. That is the idea that I want to convey, but from a mathematical, how it is from maths using
Yeah.
mathematical technique.
Mm.
Now when
Yeah.
we
So
go,
it takes element from material configuration, also gives back
yes,
in material
yes.
Lagrange
However,
form.
it's yeah, however, it's not a direct operation, right? There is two successive operations.
Correct. Correct.
Now what you see is now you get to know something some new thing here, that any tensor or vector, if it exists solely in material frame, no matter how much SRBM we do, it won't change its value or it won't change its
Because
representation.
because SFDM you are going to new configuration, no? It's
Exactly.
like
Yeah, yeah,
material is staying there only. You don't need
yeah.
material
Right,
only.
right. So which means the thing is material frame doesn't change. It will always remain the same, isn't it? It will always remain the same. That's where we started from. So this was the idea here. So we have seen two properties for now, that vectors should transform as QF, and any tensor or matrix, whatever stays in a material frame, should always the tensor should remain the same. There should be no transformation of the tensor. And one more thing we learned, which was 2-point tensor should deform according to this here. Because F is a Q 2-point tensor, so it should deform as Q into the tensor. So these are the ideas. Now let's go forward. Now let's look at some other what do you call some more what you call objective tensors. Right? Why don't we take a look at L? L was given as
Did
with
we
respect to
did we
metric.
introduce L at? Did we introduce L at?
Yes,
I
yes,
don't
yeah.
think.
No, L is just defined as the velocity gradient with respect to the spatial coordinate, right? That's why I'm using x
Yeah.
as substitute, right? Now we had also discussed, right, that f dot, which is the time derivative of this one deformation gradient, is equal to L into f. This also we had discussed. Okay, this is just a relation, and we can derive it. It's just a relation. We can easily derive it. So what we do is this implies that assuming that f is invertible and all for a general case, then L is given equal to f dot
So
into
I
f.
have this small question, Krishna, if you don't
Sure,
mind.
sure.
So f dot is time derivative now.
Yes, yes, yes.
So but L doesn't have any. Well, has velocity.
Yes,
There you have time.
exactly.
Okay,
There is
okay.
time.
Yeah.
Yes, yeah, isn't it? Now what we do is, let's suppose that L exists in the reference configuration and it's denoted by L tilde. Let it be representation. So it will be F dot tilde into F tilde inverse. This is how it will be, isn't it? This is how it will be. Okay. Now what we
Yes.
do is, we know some things, that F tilde dot is nothing
Wait,
but,
wait. So no, no, no. So
sure,
if
sure.
you take L tilde, so don't you think you should take tilde of whole, and when you
No,
subdivide it into
that
the
the thing
it
is,
would.
the thing is tilde is the value in the configuration, right? So even if you take whole tilde, it's the same as individual tildes, isn't it? Because L is just it's a multiplicative product of two tensors,
Okay.
isn't
Yeah,
it?
yeah. Okay. Yeah. Yeah, yeah, yeah. Good, good.
Yeah. Okay. So now what we have is QF is what it is. Now we'll substitute this here. Now we call it QF whole dot,
Dot.
because
Yes.
we are putting F whole dot into F inverse.
I think
F
you should
inverse
write
is like,
F. Yeah, F inverse Q inverse here. No, when you
yes.
subdivide it, I don't know. Yeah. Yeah.
This one thing, right? Now I have just put inverse. Now let's use all those properties. For the first time we need to use chain rule. So it becomes Q dot F plus Q F dot, right? Chain rule, just chain rule, pure chain rule. For the other thing, what we have is Q, sorry, not Q, it's F inverse to Q inverse, right?
Mm.
Just AB whole inverse, isn't it? Now what you see is, we know that Q inverse is nothing but Q transpose. That's from the property of orthogonal tensor. Now what? Let's multiply on both sides. So it is Q dot F. It's then F inverse. Sorry, F into F inverse.
That will be I, no? Yeah.
Plus, yeah, plus
Okay.
Q
Okay.
into F dot and F inverse Q transpose. And this also support we can't transpose, isn't it?
Why?
Just multiplying both the terms. Just multiplying. We are just expanding this.
Wait, Q and Q transpose. Okay, 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 okay. Fine, fine.
Yeah, just
Okay.
expanding this. So we
Yeah.
have two
So that
terms.
F inverse is I. Then you
Yeah, this is
finally
I.
got two times Q dot Q transpose.
And one
That
more
is
thing you look,
also.
right? Look at this and look at this.
Oh, sorry, sorry. You have F dot,
Are,
no? That is
are they
L.
they are the same, right? So it's just L.
Yes.
So which means that we had Q dot Q transpose plus QL Q transpose. You see something, right?
Yeah.
From the rule
So
which can easily be derived. We can derive it, but let's just follow the rules just to get an idea, right? We see that any matrix, sorry, any tensor which exists in reference configuration, or sorry, in spatial configuration, because L is gradient with respect to the spatial configuration, and V also exists in spatial configuration, right? So spatial by spatial will always be spatial, isn't it? There is
yeah.
no harm in that. I mean, however, we see that L tilde is not the same as, not the same, right?
Yes. Yeah. Because it has
So
velocity term in it and it is not
yeah,
objective. That's
yeah,
what you are trying to say.
yeah. So which means that any objective, what you call tensor which exists in spatial configuration should always deform. So objectivity requires, there are rules for different quantities. That's the issue here. So
Oh,
objective requires,
okay.
yeah. So objectivity requires, just a minute. So that look at in class, Kyle. No, that's in Kyle's.
I can't hear you.
Yeah, yeah. So the thing is, objectivity has it's the operations are different for different tensors and vectors.
Okay. So we,
So
we
here it
decided that velocity is not objective, right?
exactly, exactly.
And
Now you saw,
and L.
yeah, you saw something, right? So objectivity for spatial tensors
Okay.
requires that if we have some spatial tensor, say S, and we always represent spatial tensor in lowercase letters.
Yes.
So that's, and double bar indicates that it's a second order tensor.
Okay.
This should transform as Q into S tilde, so QS Q transpose. This is the rule for spatial
Correct.
tensors. However,
Yeah.
you see that it's not valid for rate of velocity gradient tensor
Yes.
because of this term here. So
Yeah,
which
I
means
think
that
it is because L also involves V. L involves V, and V
uh,
is not objective. I
yeah,
think I'm expecting that L will also not be, but we have derived it. I understand.
yes. Now we'll see
Yeah.
something. We'll see
Uh-huh.
something now. That L is not objective. L is not objective.
Okay.
So then you ask, okay, but how do I have some? But we need velocity gradient, isn't it? Because it's velocity gradient which gives us some
Strain.
rate of change of strain.
Correct. Correct.
So luckily we saw that. Why not? Let's decompose L in two parts. Any tensor can be broken into sum of symmetric plus
Correct.
antisymmetric. Any tensor. Okay.
Yeah.
Now, fine. How did we define D? And D is what is known as spatial deformation rate tensor. Spatial deformation rate tensor. And W is what we call a spin tensor. I'm sure you must be much aware in fluid mechanics, right? W W
Yeah.
W W.
Yeah. Yeah.
This is
Yeah.
that
Yeah.
WS. Now what
Gradient
is
of U plus gradient of U transpose.
no
Okay.
minus? That is W.
The minus is transpose. Yeah.
Yeah. Yeah. So here
Okay.
D is equal to half of L transpose plus or L plus L transpose. This is how do we define D. Now let's see. OK, fine. Why don't we let's evaluate it? How will D look like in the deformed config? I mean, in the after SRBM. So then it will be nothing but D tilde is equal to half of L tilde plus L tilde transpose. Right?
Yeah.
Now let's go back to the previous slide. What was L tilde? Q dot Q transpose. I'll write it here.
It will be twice. You get
Yes.
Q transpose extra, but D
Yeah. So
transpose.
Q dot Q transpose. Q
Q dot
dot
Q
Q
transpose.
transpose. Yes. Plus Q L Q transpose whole just this is for the other case we'll have
Whole
whole.
transpose. Full transpose.
Yes.
Okay.
Yeah. Plus whole transpose. Now now here the all the interesting things start coming into place. Uh, you see that Q dot Q transpose plus QL. Why not I just bring the like terms? Why just why to extend one more line, right?
Yeah.
So you see that term. This is the like term.
Yeah.
So the transpose of this is Q transpose transpose Q dot transpose,
It's Q.
isn't it? So it's the first is Q, the second is Q dot transpose, right?
Yeah. And that can be written as Q transpose whole dot, right? Because it's chain
Yes,
law.
yeah, we'll see that now, right now, yes. So here what we see is now Q L Q transpose. If you take the whole transpose of this quantity here, so it becomes Q transpose transpose, which is which is just Q
Yeah, you just get back the same
L
term. So
transpose
it's two
and
times. Yeah.
Q transpose, isn't it? Now why not separate these two out? Let's have Q as you mentioned, right? Q dot Q into Q transpose into whole dot. I mean operation plus half of, and what we'll do is we'll have Q and just take half inside. So it's L plus L transpose by 2 into Q transpose. Now you see something here that Q into Q transpose is I.
Yes.
And no matter how many times you finish with respect to time,
Yeah.
it's always 0.
Yeah.
It's a constant vector. So this term goes away. And this we recall very much from our definition here that this is nothing but D.
Yes.
So we saw something here,
Wow. Yeah. Beautiful.
isn't
D
it?
actually transforms as an objective
Exactly
term. So you can use D in our stress strain relationships.
right.
Okay,
So
great.
this is objective. So the thing is any tensor, any tensor which satisfies this relation, any tensor which is purely spatial tensor which satisfies this relation is called an objective tensor, and this can be used for our purposes. These are useful to us. So that was the idea here. Like, why is this particular tensor required? And likewise, you will see that even Cauchy stress, right? So I just now will not prove. We'll just write some things like Cauchy stress also transforms as this. This also transforms
Okay.
after SRBM.
Okay.
And so which means that this is objective.
Okay.
P, which is known as the Piola-Kirchhoff tensor, just the definitions. Will P is P, what you call transforms as Q into P. The thing is, P exists in both the configurations. Now I'll ask, okay, tell me a simple example of P. P is what you call as the engineering stress.
Yeah. So engineering stress, you will consider the area of the deformed configuration.
No, area of undeformed.
Oh.
Yes.
Okay. Fine.
Yes,
Okay.
area of undeformed. So area of undeformed, but the force lying in the deformed configuration.
Yeah. Yeah. Exactly. So in one time
Yes.
you consider force and by same area, but sometimes
Yes.
take undeformed area. Yeah. So I've got
Yes.
yeah.
Yeah.
Okay.
So this is what you call as the true stress, Cauchy stress.
Yeah. Yeah. True stress is you take real area. Yes. Yes.
Yes, real area. But the thing is, real area is difficult to measure
Correct. Correct.
when we do some experiments, right? So we always stick with the
Yeah.
original
Even
area.
in solid mechanics, I remember.
Huh.
So there is this one example where you have a beam
Right,
and
right.
it has been acted upon by force.
Huh, huh, huh.
Once you apply the force, this beam starts to deflect
Yeah, yeah,
and it deflects. And and suddenly, so even if it is deflecting, you consider the force to be normal to the surface, right? So since
yeah.
it deformed. So it is no
Hmm,
more on a straight line. It deforms
hmm,
and even the force acting will also be in different direction now.
hmm, hmm, hmm.
But people don't, for some reason they don't consider it as deformed. They don't consider the force is
Exactly. Yeah,
no
yeah,
more in
yeah.
one direction. It is in angle
Right,
direction. If you
right, right, right.
and they consider the area of the initial configuration because it is easy to just straight line and just take
Exactly,
area.
exactly, exactly.
That.
And
And
for
I'm
us,
like,
it's all about things which can measure, which are relevant to us, isn't it? Otherwise, so then we use all such transformations and get back what we want or get back what we need, isn't it? As per our requirement. Okay. And you see that there is something known as a second Piola-Kirchhoff stress,
yeah,
and that
yes, you
is
say.
defined as S is equal to S tilde is also equal to S. So even S is objective.
Okay.
So like these
Okay.
are all objective force. So these are the ones which we, so any constitutive model, you will see that this is how we relate to things. I mean, we require some measure of strain, some measure of stress, and get what we want.
So how is P Q P? Why are we missing Q transpose over there as well?
This is 2-point tensor. Remember, right? This P happens to be 2-point. So I'll
Oh, it
write the
has to
general.
act on. But Q sigma is also
No,
Cauchy stress is also
yes,
2 point. No.
yeah. The thing is, 2-point means points in which reference. If the say in this case, force also lies in reference in the spatial, and even area lies in spatial
Correct.
for Cauchy stress. So that's why it always lies in spatial configuration. Force in spatial. Yeah, there is the idea.
Okay.
There is the idea. Yes.
Okay. So what? Okay, now I understood. So objectivity has certain rules. Like if you
Yeah,
take a
certain rules.
first order tensor, then for it to be, if
Objective.
you take a vector which is staying in
Yes.
spatial frame, then
Yeah.
for it to be objective, then it has to transform like q times x.
Exactly.
That's one
Yes.
thing.
Yes.
If it is
Yes.
staying in spatial form, which if we have discussed like q, v doesn't satisfy that. All the stuff we have discussed. So when you
Yeah.
take 2 point tensors, and the 2 point tensor, depending on the nature, like if it is going from, if the 2 point tensor is from reference to space, or if it is from space to space, or from reference to reference, depending
Right.
on those three things, I think the objective rules will change. And
Exactly. And
here
these are the rules.
and here, the first Piola-Kirchhoff tensor, I don't know if from where it is to. I don't know if it is from reference to spatial or from spatial to reference.
Yeah, it's the
So the
first.
objective, Okay, so the objectivity rule is it is QP, and for second Piola-Kirchhoff tensor, I think it is only in material frame. I think S is
Exactly.
only in like from material frame to material
Right.
reference to reference. So the
Right.
objectivity rule should be S equal to S, and it
Just
actually
S.
satisfies that. Great,
Yes.
awesome,
And for
awesome.
vector, these are just the rules. I mean, you just need to remember the rules. And the thing is,
Okay,
we know how to derive also, so there is nothing to worry. We should remember
great,
and know how to
excellent,
derive.
excellent,
Isn't it?
excellent. Yeah.
And there is one more thing here. For scalars, you don't require anything. It should be the same. So
Yes,
rho
it's like
tilde,
temperature. Yeah, absolutely.
because for spatial, we don't need to worry about what you call any deformation, right? I mean,
So
it expressed, but the thing is just it purely rotates. So
yeah,
temperature tilde will also be temperature. Pressure tilde
correct.
will also be pressure. And
If you remember our scalar transport equation, mass material scalar transport, which
yes,
was rho equal to J times rho dot rho, if you remember, rho dot equal to J
right.
times
Yeah,
V
rho
equal
dot is plus
not
j.
rho dot,
Sorry,
not
rho divergence of v is equal to 0, something like this, right?
this is scalar form. In material form it was J times
Yeah,
rho zero, right? Rho
yeah, then it
equal
is
to,
just rho is equal to rho naught. Sorry, rho j is equal to rho naught, and j
very
is
good.
determinant of f.
Yeah. So if can we, I mean, I'm
Yeah, of
cutting
course,
the, I mean, I'm deviating from the
of
class,
course,
but I think if you actually look at if this actually satisfies objectivity,
of course.
I think
Yeah,
you should,
it
right?
yeah. Let's see. Why not? Why not? Then
So
in that
here,
case, j tilde
so
will be equal to
yeah,
determinant of
all thing we should see is if J tilde is satisfies or not,
yes, yes. So we see that j
because
is
rho is automatically same.
right, right. Now you see, right? J is equal to j tilde is equal to determinant of qf, and determinant
Maybe
of q is 1.
AB is equal to, okay. Yeah, I can't
Determinant of
see the, okay, didn't write.
the
Sorry.
determinant of q into determinant of f.
Yeah,
Determinant of q is plus 1.
yeah, and it is a determinant of F. Yeah, exactly.
Yeah. So j tilde is
That's
equal to j.
okay. So in the same way, I don't know if the scalar,
Of course, we can pose that. You see, right? What we do is we have rho tilde j tilde is equal to rho naught, and this will be the same as rho into j. Fine.
yeah,
So since both are equal on both sides, then rho tilde and j tilde is j. This is equal to rho j. J cancels out. So it means that rho tilde is equal to rho.
yeah, cool.
So it's a simple proof here. So it should be true.
Awesome.
So now we have understood what we mean by objectivity. So essentially, this is objectivity. Now let's follow our discussion and slightly, I mean, not deviate, because the thing is then principle of virtue will be a deviation from here.
Yeah.
So why not we just
Okay.
let's
Good.
continue with what we call as the objective, what you call the work conjugates. And the thing is,
Okay.
we'll only deal with simple, just we'll not go through the detailed derivation, because then detailed derivation doesn't have much to say. It's the ideas which are relevant to us right now. So
Okay.
yeah, so we'll just go through the ideas per se.
Yeah.
Okay, and here is my notes. I think we are on. Okay, yeah, I think yes. Okay, so let's pull out the 41, 2, 2, down. Yes, we did. Okay. So what we'll do is let's just discuss about something about work conjugation. Now, what does work conjugacy mean?
So
Now,
conjugate generally means it's like complex number, right? Conjugates are here.
yeah,
Conjugates in complex.
yeah, that's in one context, and in other context here, we mean. what are the equivalent, like for a particular stress measure,
Okay.
what is the equivalent strain measure which gives us the value of work,
Oh, okay.
isn't it? So what we'll do is let's start with spatial virtual work expression. In this case, delta W is equal to sigma dV. Now this dV is the elemental volume, and this sigma is what we call as the uh, stress, as a Cauchy stress tensor. Now what we see is this is equivalent to partial B. Okay, I think we really need to go to virtual work principle. So what
Okay.
we do is today is, I think let's just do the virtual work and we'll return to it here again later.
Or can you go to the contents once?
Sure.
Like what we want to discuss today.
Yeah,
So so Piola-Kirchhoff is done, right? That's what you're
yeah,
telling. Like
yes, that,
top
yes.
Piola-Kirchhoff is
Yeah.
fine. And decomposition of stresses, is it also same? Like it's okay?
The thing is, decomposition of stresses is just to what you call decompose any stress into two components. One we call spherical part, and one is the
Uh-huh.
deviatory.
Okay. Yeah, I know that.
So these are
Yeah.
just like three expressions. The detailed derivation is in the notes
Yeah.
because if you repeat notes, then
Minus
I think
P. Correct.
yes.
Minus P plus they write something.
Yeah,
Yeah.
exactly.
Objective rates.
Objective rates is how do the rates of tensors. I mean, what is I mean, then we are looking for rates which are also objective in nature. So what we later see is even
Oh,
sigma dot is not objective. So like
yeah.
sigma dot tilde is not the same as q
Yeah.
sigma dot q transpose.
Okay.
So that's why you'll see that in all these finite element codes and all that, you will see that we are not actually doing time rate. We actually use a very different time rate.
Okay.
The thing is, we don't come across much because we are not working in plasticity and all that, where the thing is even rate of change of stress starts mattering.
Correct. Yeah.
Then we'll see that we need to construct a new rates. So you'll find that in a vertical when we have non-Newtonian fluids and all that, viscoplastic, viscoelastic fluids, then in
Okay.
that case, we actually have to have the rate of change of stress coming into the picture. And then we have different rates we call as Aldroyd rates, Jawman rates, Truesdale rates. There are a host of rates. In this lecture, we are dealing with 5 different rates.
Okay.
And then this is all in, I think, different contexts.
Okay. So we will not discuss second and third one. Okay. Is it fine?
Yeah. Okay. What we should do is let's have one extra class actually. What do you
Sure.
suggest? Somewhere in between so that we'll just cover it up and then we can go to the next
So,
class.
uh, so do you want to stop here or like what?
Yeah,
I
I
don't
think
know.
because I think I have filled your mind with too many terms today.
No. It's no. It was great actually. Great
Yeah.
class. I loved it. I mean, I'm
So
very clear about what the objectivity is now. Like I
yes.
understood.
Yeah.
Like now I will see that why we should only use some terms in some constitutive laws. Like why can't we
Exactly.
use something else? And that's the
Right.
whole point of objectivity. And
Right.
so I have one more question. Why are we not discussing entropy at all? Because entropy is constitutive laws. You need entropy, right?
Yeah, actually the thing is that's the problem with such courses, right? We don't do complete things.
Yeah.
That's again a disappointment. Yeah. The thing is, and also the thing is, we cannot complete that because the instructor has clearly this one, right? Is specified it's computational quantum mechanics. So
Mm.
what we will do, right? Both of us, we will actually review second law of thermodynamics. I
Yeah.
have some
Yeah.
very good notes. Actually,
Yeah.
it's
Sure.
published by University of Auckland. These are, I mean,
Oh,
that those are the best notes I have found ever. I mean, on quantum mechanics. So we will very simple to read. We'll do from there.
sure.
Okay, so what we do is, should we just stop recording and then maybe discuss those notes? I mean, just look at the
Yes.
note.
Yes. We will stop recording here.
Yeah,
And
and let's just, okay then. So let's meet during next week. Okay, so I will stop.